All right, welcome to Chapter 19 for Geography 201. This is Chapter 19, which is all about the coasts. It's also the last lecture of the semester. I always kind of find to kind of end up talking about beaches. So when we talk about coastal processes, we're going to start out talking about tides, waves, and longshore currents before we get into actual beaches. But tides. So tides are this uh, twice a day change in the level of water of sea level, which is caused by the moon and the sun's gravity pulls. And one of the reasons this is important is that when the tide rises, it actually allows water to reach further inland. And so it increases the range of coastline that is influenced by the oceans when it comes to forms. And interestingly enough, even though the moon is much smaller than the sun, because it is so much closer, it has a larger pull. The moon and the sun both do influence tides, but the moon is the dominant, in fact, twice as much. So you can see right here that the bulge of water which causes the tides is bigger facing the moon than the side facing the sun. Now, understand this is a greatly exaggerated. The tide or the moon's gravity does not pull the Earth's water thousands of miles into the air. But what it does cause is the oceans to slightly bulge on that side. Um, Maybe 20 or 30 feet higher than they would normally. And as the Earth rotates, right, we know it rotates actually this way, right? As it rotates, we're looking down at North Pole. Right now, this little where my cursor is, now it's at low tide, and now the tide rises, and the tide falls, and the tide rises, and the tide falls. So to us, it appears like the water is going up and down, but in reality, the water is kind of staying there, and we're moving through it. It's kind of like how it looks like the sun rises, but in reality, the sun is staying there, and we're going around it. So the sides happen twice a day. The way the Earth rotates, they're high twice a day and low. And you can look right here at this part of Kodiak Island. This is a graph. It tells you the height. And you can see that it's highest, high tide, when it's facing the moon. And when it's opposite the moon, it's lower. I'm going to show you what that means in a little bit. Because the sun and the moon can either work together or they can work against each other. And that gives us the idea of spring or neap tides. So spring tides don't occur just in the spring. It's basically alignment. When the sun and the moon and the earth are all aligned just right, the forces that create the tide, the gravity is strongest, and so we call these spring tides. They are the highest tides. Okay? Now conversely, if the moon and the sun are at right angles, they kind of contradict each other, and they produce the lowest tides. And those are called neap tides. So here's what it looks like. If the sun and the moon are on the same side of the earth, they're in line, their gravity is strongest here, so this is the highest tide. So any area that experiences a tide right here would have their spring tides. Okay? Now, later on, about 7 days later, the moon is here in relation to the sun, and so the bulges you see are smaller. So when the moon and the sun are at right angles like that, that's a neap tide. That's the smallest bulge of water. Now over here you have a spring tide. They're in alignment. They pull again. When they're opposed to that, and that's how that works. Now notice here 7, 14, 21, 28. The moon takes 28 days to rotate around the Earth. That's why a lunar cycle takes 28 days. So if you ever notice, we have a full moon, and then it basically goes from a full moon to no moon every 28 days. And the tides kind of tie in with that. So because we know that the moon and the earth rotates every 24 hours, right, that every 24 hours we have two tides. So for 6 hours of the day, the tide is coming in. So if you're at the beach, right, and the water's getting higher, it looks like the ocean's flooding you out. They call it a flood tide. The water is rising and it's coming inland. Conversely, when the tide falls or gets lower, it recedes or it ebbs away. So we have flood tide and ebb tide, roughly twice a day. Now, I said spring tide was a high tide. Spring tide is the highest tide. But every day, high tide is how far does the water come up that day. and the peak is high tide. How low does it go every day? And that lowest drop is low tide. So you have that area. Now, you have the difference between high tide and low tide. So this is an area that is sometimes wet, sometimes dry. They call it the intertidal zone. So the question is, how high are the tides? Well, that depends. There are many things that affect it. It's not the same everywhere. The body of water is the ocean. Smaller bodies of water, like the Great Lakes, the Mediterranean, don't have as strong of a tide because the oceans are larger. It's about the size of the water. If the wind is blowing, it can actually blow water in and help it lift. If there's a hurricane, that can do it. And then the big thing is they call it the bathymetry, the shape of the seafloor. So you see on this map, the darker red areas have higher average ranges, or in other words, difference between low and high tide. The biggest difference, though, in the world, it's kind of hard to tell, is right here in the Bay of Fundy, because the average high tide or tidal range is about 3 feet. That's the difference. But in the Bay of Fundy, which is right here off of the coast of Maine, you can get as much as 55 feet. And it's because of the shape of this bay. So when high tide comes in and the water comes in, it goes up this bay and it pushes all that water ahead of it, and this says high tide. So the tides actually are higher here. You can see at the head of the bay almost 50 feet. So here's an area at low tide. You can see the people working right there. Those are people. And then at high tide, the water comes up to these notches. So I actually found this really neat time-lapse video. So this is over the space of a day. There's the water coming in, and the boats are going up. And now we are at high tide, and now the water begins to fall. So let me go back to that again. So this is low tide. Notice this boat. This is a large, big fishing boat sitting on the ground, and here's the top of the dock. So this is low tide, and notice how high that water comes in. So you can see that area, the tide is extremely variable. The next big thing that affects beaches and coasts are waves. So waves happen anywhere there's water and there's wind. And what happens is, as the wind moves over the water, the friction actually basically pushes the water and it transfers the energy of the wind into the waves. So it's friction. It's wind force and friction. Now, most of us think of waves kind of rolling forward, but in actuality, a wave is what they call a wave of oscillation. In other words, and I'm going to show you in a little bit, if you've ever been in a wave at the beach, you notice the waves may push you a little bit inland, but they actually have more of a vertical movement. We'll show you that. But how big do waves get? Well, that depends. The height of the wave, so the difference between the lowest and the highest point of the water, how strong is the wind? Stronger winds blow more force, they have more power. Also, how long does the wind blow over the water? The longer the wind blows over open water, the more movement it can transfer, the bigger the waves get. They call that fetch. How far is the fetch? So that's why waves are largest in the middle of the ocean, because they can blow for thousands of miles. So waves are created circular motion. And this just shows you right here. These little blue dots represent individual molecules of water. And watch as a wave moves through. Watch the motion. So the wind blows and pushes the wave. And if you trace their path, you notice they go in a circle. Up and down. So the wave actually says right here. So let's watch that again. So the wave actually, the movement of the molecules, the water pretty much stays in place. It's this movement that pushes the molecules next to it. The molecules themselves really don't travel. But notice, before I start again, that every circle, right, that travels this one, the next circle down is a little smaller. See? Smaller, smaller, smaller. Finally, at a certain point, there is no. So, out in the open ocean, these waves can be quite large. But what happens when they get close to the shore is that that area for that wave in the water, it gets less, right? As the shore, as you get closer to the beach, closer to the shore, the water gets shallower. And then what happens eventually is that wave pattern will hit the seafloor. And what happens is, I'm going to show you a picture, that's when waves start to break. So when the wave pattern, the circular movement of the water, when it comes in contact with the bottom of the ocean near the coastline, this slows it down. The top half of the wave begins to move faster than the bottom, and eventually falls over. It goes from a wave of oscillation to a wave of translation and a breaker. So here's what I mean. Out here in the open ocean, right? Here's the circular patterns. Goes down about this far. And usually what they look at is this. If you measure this wavelength, the difference between this wave and this wave, that's the wavelength, or distance between 2 points on a wave. This is usually about 2/3 or 3/4 of that. So below this line, the water's not moving. Now, when we get close to shore, notice now it comes in contact. And what happens is these patterns still work, but the circular movements move faster here, but slower here, because here they're hitting the bottom. And so it begins to lean forward. And that's when you start to see the waves kind of do that little grow and grow until they finally break over. And they are literally falling over. That's why they call it a breaking wave. So when you see waves begin to have that white little crest, that's when they first contact the bottom of the shoreline. One of the things I have you do, or we don't do this semester, is go for your scavenger hunt and go to the beach. So you can sit at the beach and look offshore and watch the waves come in. And based on how high the waves are, you can guess how deep they go underwater, and you can see where they hit. You can often see like shallow little areas off in the lake because the waves will crest. The last part is the breakers. Let me go back to that. When the wave falls over and breaks, that big huge curve, that's called the breaker zone or the surf zone. That's the part that we like to run in back and forth and play, right? So as the waves fall over and break, right, they kind of come up the beach. That's the swash, the rush of water coming up the beach. And then they go back down, and that is the backwash. That is the fancy scientific name. Now, another thing that happens with waves, too, is that shorelines are rarely straight. So when the shoreline is curved like this, it makes waves curve. Out in deep water, the waves all move parallel to each other in lines. But when they hit shallow water, they start to slow down. So if you have an area here that sticks out into the water, and this area goes in, it hits shallow water first here, so it slows down here. So it allows the waves to actually start curving, because these waves are slowing down, and they're slowing faster than these waves, because the water is deeper right here, in between those 2 points. And what happens is it causes the waves to basically bend around the coast. So it looks kind of like this. Waves usually end up hitting pretty much parallel. And the last wave action here is the longshore current. So most waves do not come in perfectly perpendicular to the beach. There's a little bit of an angle. Maybe not a lot, maybe a lot, but for rarely ever are they perfectly perpendicular. And what happens is they create what's called a longshore current. Most sandy beaches with waves have a general current in the water that flows parallel to the beach. And that movement also brings sand and sediment with it, which is the longshore drift. Okay? By the way, this happens both on water and on top of the water. So here's what happens. Here's your waves. They're coming in a little bit of an angle. They're crashing on the shore, and they go crash up, right, the swash, and back down. So when they crash and they go up the beach, they go up at the angle that they came into the beach to. So this is, you see, is how it's kind of this angle here. They're coming in at an angle. Now when they're done here and they go back, they follow gravity. So now they flow this way, but straight down the beach. Straight down the beach. So over time, the waves do this: up, up, down, and that zigzag creates a small current in the water that generally moves the water this way. If they were heading this way, the current would be going that way. So there's usually a longshore current. It's not very fast, but enough that it drags some sand along with it. And you can see right here that it'll actually create like a sandbar. It's dragging all this sand and dropping it right here. So as it washes up against the coast, it builds this kind of barrier island, which we'll talk about in a little bit. The one opposition to this is the rip current. So sometimes, we go back to that longshore current, there is a current that goes straight out from the beach. And so generally speaking, the currents go this way, but there's a current that goes straight out. That's a rip current. And what happens is, when the waves are piling up on the beach, maybe like in a really windy day, all that water is being pushed towards the beach. It's actually more water out there. It's a little bit higher than in the lake. It wants to come back out. But there's water behind it being pushed on shore. Let's go back to that image. So say the waves are coming this way constantly, and the water wants to come back out this way, but these waves are stopping it. Something happens, a break in the waves, maybe there's a gap under the water here, a deeper part of the soil, and the waves come out, and that's when we get rip currents. And these are very dangerous, not because they're so strong, but they're enough that people panic. What happens is, go back to that image, you're out here, you're swimming in the beach, the waves are coming by, and all of a sudden you get stuck in a rip current. And the rip current doesn't go this way, it goes straight up to the deepest water. So all of a sudden now, you're sitting there and you get pushed out into the deep water. So what's your first instinct, right? You want to swim back to land. That's your first instinct. Well, now you're swimming against the current, which is much harder. And so what ends up happening, people die in rip currents in Lake Michigan every year because they try to swim back to the shore. But rip currents aren't very wide. The best practice is honestly, if you're being pushed out into the lake, you just lie on your back in your float and you swim across the rip current. So again, one more time. There's a rip current here. Instead of fighting it going back to the beach, just swim a little bit this way. Because rip currents are not that wide. And once you get over here, you're out of it and you're fine. So the sad thing about rip currents is they're one of the major killers. Every year in Lake Michigan, more people die in Lake Michigan because of rip currents. Lake Michigan's geography favors them quite often. Whenever we have windy storm days, you'll see red flags. It's for the rip currents. But the sad thing is, if people just knew this and would just swim across it, they'd be fine. All right, we're going to pause here. So I'll come back with part 2 in just a moment.